Howdy everybody, my name is Jonathan Medrano, and today we'll be looking at the analysis of a skydiver in freefall. Part 1. So for the description of a system, I chose to analyze a skydiver in freefall. He has yet to reach terminal velocity and he just jumps from a height of 500 meters. So according to United States Parachute Association, 1 in 1,000 parachutes fail, which is only going to be 0.1%, so this is quite rare. But if the skydiver were to experience a complete parachute malfunction, how fast do they need to react before impact if jumping from 500 meters? So what we are going to do is use Simulink to plot the position, velocity, and acceleration versus time. So some assumptions we made here for the design parameters. This is going to be an ideal case, as the model ignores negligible details of natural process. So obviously no relativity. The user here is moving at earthly speeds, nothing near the speed of light. It's going to be a lumped mass parameter, as in the mass is going to be assumed to be just a point mass system. This is so that the drag coefficient isn't anything crazy, because everything changes with the shape of the person. So it's also going to be linear forces only, nothing in the x and y for this first part. Nothing in the x for this first part. And our initial velocity is going to be 0, because it is the peak of the elliptical. So we're also going to assume ground is the origin and down is the positive direction. So for the model of the system, our equation of motion, we have the sum of the forces is equal to mass times acceleration. The forces here are going to be Fd and Fv, where Fd is a force due to gravity and Fv is a force due to drag. Now don't worry, I know that we should have a minus Fv, but I'll talk about that right now. So in this model, the air resistance can be assumed to be linearly proportional with velocity. So Fv is going to equal to negative Cv. So the negative didn't go away, that's just how we named the variable. Finally, with this information, we can derive the equation of motion, which is the change of velocity over change in time, is going to equal gravity constant minus our drag coefficient times velocity divided by the mass of the user. So our m is going to be 70 kilograms and our c is going to be 12.5 kilograms per second based on data from a previous experiment. So for our initial results here, we see that for the position versus time graph, he's jumping from 500 meters and he hits 0 at about 14 seconds. That's not very much time to react, assuming that he needs 100 meters to open the parachute. He hits that distance at around 12.5 seconds. So he'd only have about 2.5 seconds to, not even that, like 2 seconds to deploy that parachute, which is not a lot of reaction time. That's why you see they need to go through quite a bit of training before skydiving. Here we're looking at the velocity versus time graph. We can see that terminal velocity isn't reached within the 20-second period of the simulation. And yeah, looking at this last acceleration versus time graph, it again shows us that terminal velocity is not reached, because if terminal velocity is reached, the drag force is going to equal the weight, and then the user is in free fall, so they are no longer accelerating down. They'll reach terminal velocity, which they have yet to reach here. Now, unfortunately, I underestimated the calculations here, so with this new information, we can go back and adjust the drag coefficient in order to see what the speed the user hits the floor. And I would like to incorporate a nonlinear drag. So for this first part, going back to that initial question, we see that this user does not have a lot of time. He has about 2 seconds of reaction time. So given that, I'd like to conclude this presentation. Thank you for your time. And do we have any questions? Thank you.